to properly introduce David, we have the head of school, Gareth Harrison, who's going to say a few words, and then David will begin.
Oh, thank you very much, Ian. Welcome to those online. I know, Ian, I think your parents online. Jackie and the rest of your family here, welcome. You can see what he does for a living now. So it's, thank you to Louise, who's organised this, as usual. And I think this is going to be a good one. There's no demonstrations of this one, but you're going to get lots of interesting computing. And David's been with us since 2006. I actually am shocked. That's such a long time. But it's been a good one. I really enjoyed working with David. He's been a phenomenal colleague. I've learned a lot from him. He's involved in all sorts of random projects in Europe. I think probably looking at his biography, it's a phenomenal one. I think the standout one for us, I think, is his leadership of ID Core, for which I think he'd be rightly applauded. And it's only won it 3 times, so I think that must be a record. But otherwise, he's been very heavily involved in things that go bang in his earlier lives, things that go swish, and I'm hoping we're going to see more of that today. So, good luck.
Thank you very much. So, good evening, ladies and gentlemen. It's a great pleasure to be doing this. It seems a long time ago that the chair was awarded, but we used to only have one lecture theatre, and then there was a queuing problem. So now we've got this wonderful new building. The queuing problem is resolving itself, and I'm getting to do this, and I hope you're going to find it interesting. So we're going to go on a bit of adventure. We're going to talk about some fluid mechanics. We're going to talk about some computer science, and we're going to talk about some numerical analysis. And I apologise to my family if they've heard lots of this before. We once had a dinner conversation over dinner, and one of my sons said, "Can't we talk about something normal at the dinner table?" So we said, "Well, what do you want to talk about?" And they said, "I don't know, something normal." And after about 10 minutes of silence, we went back to talking about physics and maths and computing and engineering and all sorts of stuff. So I apologise if they've heard this before. None of what I'm going to talk about happens because of just me. This is very much a collaborative effort, and so there are a huge number of people that I ought to be thanking, and a few of the names are on the list. I want to start by thanking my mum and dad, not for the obvious reason, but thanking my dad for buying an Apple II computer, probably in about 1979, 1980, something like that. It saved my life. And I want to thank my mum for fighting very, very hard for support for their dyslexic son at school, because that made a big difference as well. And the third person on that list is my great uncle, who was a civil engineer and a bridge builder, did the steelwork design for the Forth Road Bridge. He's probably a bit more famous for building the Hooghly River Bridge in Calcutta and various other things. And when I was about 14, he came down to visit us in Plymouth, and we spent an afternoon talking about all sorts of strange things to do with engineering that was not really about engineering, but was a lot about problem solving. And I think that was a bit of a push in some directions. Mark Cross and Richard Merritt are 2 inspirational teachers who got me started. Mark Cross was a professor at what was then Thames Polytechnic, and Richard Merritt was a school physics teacher who let me play with computers and do all sorts of strange things and install computer networks at the high school and do all sorts of weird things. Alan Burns and Ian Jones are on the list. They're the people that introduced me to computational fluid dynamics when I worked at Harwell, and I wouldn't be here today if it wasn't for them. The next group, apart from Bill at the bottom, is family. I put MI Chemie after Jackie because she's the real engineer in our family, and I'm not. I just work in a school of engineering. I'm really a mathematician. Bill Griffiths is a great friend, and it's important to have people that you can talk to who aren't engineers, who aren't mathematicians, who aren't scientists. He's an archaeologist, and we talk a lot about all sorts of random stuff, and it's quite good. And then the next group of people are the people that got me involved in waves and wave breaking and starting the kind of research that I do. And it's Tom's fault that I'm here because we worked together on a project with William. The Boyan Zhang's my first PhD student. You'll see some of his work later, and I also worked briefly with Tito Toro when he was at MMU. And the next group are the amazing people from IES and the School of Engineering who've given me huge amounts of support and stuff at various times. And the next block are the people that make ID Core the success it is. They'll be disappointed that I'm not going to talk about ID Core. And then I have my Japanese friends who are very important in all of this, and I will be seeing very shortly. And then a group of people that have worked with us on tidal turbines and stuff. Some of them whom are in Chile, and I know are joining in online from Chile, and some of whom are in the UK and France, and then the funders who've given us money, because without money, none of this happens. Okay, so why is this called discontinuous? Well, to start with, lots of people have said this, but I found this quote: breakthroughs in science often happen at the intersection of diverse scientific disciplines. And if, like me, you get bored easily and you want to be interested in things, then keep finding joins, because it's very interesting to be at those things where you bump into something else. And so that's been very important. And the other reason it's called discontinuous is because of this. We went to see the film Up, the Disney Pixar film, some time ago. And there's an important character in Up called Doug, who is a dog. It has a box around his neck that interprets what the dog's saying, so it speaks English. And all the way through the film, at various points, the dog shouts squirrel and just goes into this pointer pose and starts looking at things. And when we came out of the film, my sons Rowan and Laurie were laughing hysterically all the way home from the cinema and pointing at me and laughing. And they said, "You're just like that dog, Doug. You can't concentrate on anything for 5 minutes until you see something else and it's a squirrel." So that's also why this talk is discontinuous. Okay. I promised an adventure, and if we have an adventure, we need a map. And who better to provide a map than Charles Dodson, better known as Lewis Carroll. In The Hunting of the Snark, he says, he had brought a large map representing the sea without the least vestige of land, and the crew were very much pleased when they found it to be a map they could all understand. So hopefully we're going to not have quite such a blank map, but I'm going to talk about things. Now, Ian's a mathematician, so I thought I'd better start with some mathematics. If we're going to talk about discontinuity, we need to talk about continuity. And so I've put some maths on here. It's a load of squiggles to most people, but what it tells you is that a line is continuous if, as you approach each point on the line, then the point that you're approaching is the point that you get to, effectively. So you can draw the line without taking your pen off the paper, and that's what all the squiggles at the top say. If that's what continuous is, then discontinuous is that there is some point on that line, at least one, where you have to take your pencil off the paper, where the value of the function, if you approach it from the left, is different to the value if you approach it from the right. And then we have a jump, we have a discontinuity. And that's what we're going to talk about in this lecture. Now, discontinuities occur all over the place. We see lots of discontinuities. So here is several discontinuities in a picture. We've got a discontinuity in the landscape. There's some cliffs. If you were walking along, you'd suddenly fall off a cliff. There's a sudden change in altitude. Also in here is a wall. It happens to be Hadrian's Wall in Northumbria. And if we think about Roman power as we approach the wall, then on one side of that wall was the Roman Empire, and on the other side of the wall wasn't. So you've got a discontinuity in political influence as you go across the wall. Now, I'm going to talk about more physics-based shockwaves than political ones. So let's start with this, which is a cannon going bang. I was told some time ago, actually by the late Ian Bryden, that if you gave an inaugural lecture, it should be very Royal Institution Christmas lecture. And the Royal Institution Christmas lectures always has to have this strange man called Mr. Coates who brought on an experiment that usually went bang. They won't let me set a cannon off in here. It's very loud. But when that cannon fires, and this is one of the cannons of the sealed not firing, when that cannon fires, we get a very loud bang that you'd hear. What's happened is that inside the barrel of the shockwave, a shockwave has been created, And that shock is a discontinuous change in pressure, which is traveling at more than 300 meters a second as it comes out at the end of the barrel. And you hear that as the bang. So let's think about this a bit more. Let's have a gunpowder activated shock tube. So I'm going to have a steel tube with one end blocked off, and I'm going to fill part of that with gunpowder, and I'm going to set fire to the gunpowder. It's going to burn very quickly and almost instantaneously turn into a very hot, high-pressure, high-density gas. And that gas has got to go somewhere, so it's going to expand out of the barrel because there's a steel plug screwed into the other end. And this is one of Rusty Aldwinkle's photos of me firing a musket. It's actually a 17th century carbine. Somebody asked me if we could have dragons in the lecture. I am a dragoon, and that is a dragon. Okay. If we think about the physics of what's going on, we could draw a diagram a bit like this. This is a few microseconds after the gunpowder has burned. So we have high pressure gas that is expanding into a lower pressure gas as we come down the tube. And then we've got low pressure gas state, and then that low pressure gas bumps into the air, which is being compressed by the shock wave moving down the barrel. And that compressed air eventually then has a shock wave which meets the undisturbed air. Between the burnt gas and the compressed air, we have what we call a contact discontinuity. And if we want to represent that on a computer, then we have to divide space up into a load of chunks, which we call grid cells, and we're going to have those of some fixed width or some variable width, delta x, that we're going to have. So we divide space up like that. And what I'm going to do now is in each one of those little volumes on the computer, I'm going to store the average value of the density in that grid cell. Or it might be the pressure or the velocity or the total energy in the gas is going to get stored there. And now we can start trying to solve the physics equations to tell us how this changes in time and run that through the computer simulation. Here's some complicated mathematics. It's not too bad. Written at the top there in a conservative form are the Euler equations. These are equations of gas dynamics which were written down by Leonhard Euler in the 18th century. Euler's a very prodigious mathematician, and there's hundreds and hundreds and hundreds of things that he's done. And he wrote this down, and he wrote a treatise, and he said that about wraps it up for fluid dynamics. There's nothing else to be done now that I've written down the governing equations, because he was quite a modest man. He actually made a mistake in the governing equations. He didn't know about internal viscosity in the fluid and internal friction in the fluid. And so it was sometime later that we ended up with the Navier-Stokes equations, which include those. But from our point of view, the important thing about this is that those equations more or less say mathematically that the rate of change of the quantity that's conserved, density, momentum, or energy, that is we can just represent that by one of those little volumes and say what's coming in minus what went out is what the change is. So that's what that top set of equations does. And what we can do then is we can write that in a simpler way, and we can say if we know the flux on the left-hand side and the flux on the right-hand side, the difference between those two fluxes must be the change that's gone on. So the question is, where do we get that from? So I want to introduce you to a Russian called Sergei Godunov. I met Sergei. We held a party to celebrate his 70th birthday when I was in Manchester, which he came to. And he told us that he hadn't worked on shockwaves since the 1960s. But it was interesting to meet him. And he had the idea that you could use physics and solve something called a Riemann problem, which is that little cartoon at the bottom, to find out what's happened at the interface between the grid cells. And essentially, we've got different waves traveling at different speeds, and between those waves we have states, which might be left-hand state, right-hand state, or some intermediate states. And if we can solve those equations, we can work out what the change is and sum that up in our computer. Tito Toro had the realization that you could do this very efficiently by trying some approximate problems that got progressively more and more complicated. And so you could do more work in places that was difficult, and you could get a really easy answer in places where nothing much was happening. So we used that idea. So if we go back to the computer problem, we've now got these little Riemann problems at the interface between all the grid cells, and we can add up all those changes and work out what's happened to the solution and move forwards in time. And this is a first order solution, and so we need a very, very small value of delta x to advance the solution accurately. Alternatively, we could join them up not with constant values, but we could use linear interpolation and slopes in between all the grid cells, and that would give us a better solution. But unfortunately, Godunov proved, and mathematical proofs are annoying things because it absolutely means it will happen and there's no alternative, that you get oscillations. So the graph on the left-hand side here, you can see you've got some strange oscillations around the shock waves, and on the right-hand one, they've been smoothed out because a mathematician called Amy Harton showed that we could smooth those out by dropping the order of accuracy if there was going to be an oscillation. So that's the kind of method that we are going to use to solve these equations. So I'll go back to the musket simulation. My gun takes 5 grams of gunpowder at a time. That fills the last 10 millimeters of the barrel. The barrel's got a radius of 8 millimeters. Gunpowder has an energy density of 3 megajoules a kilogram. So one charge releases about 170 kilojoules. And I can use that to find the pressure in the burnt gas and the rest of the tubes at atmospheric pressure. And we can solve all those equations, and we get curves like this for the pressure, the density, and the velocity inside the gun barrel. So we've done a little experiment, and we've got our numerical simulation of the gun firing. Shock waves in 1D are very boring, so we're not going to do any more with those. You will have seen an image very like this on the flyer for the talk. This is a shock reflection. It's called Mark reflection, and it was first described formally by Ernst Mach. As a shock wave propagates along horizontally, if it bumps into a wall, if the shock wave is going at the right speed, then a shock wave forms which is at 90 degrees to the wall. It has to be normal to the wall. That's called the Mach stem. And in this picture, you can see the Mach stem. You can see the incident shock traveling along into the dark blue, and you can see the reflected shock wave. And then in the density picture, you can also see the contact discontinuity. If we go very, very quickly, this shock wave is traveling about twice the speed of sound. If we go very, very quickly and we travel at nearly 9 times the speed of sound, then we get double Mach reflection, and the shock structure is a lot more complicated. And I computed both of these using the Amrex solver just a few weeks ago, and these calculations took about 8 hours each to run on this laptop computer. They're using a technique called automatic mesh refinement, where the grid is made fine in regions where there are sharp discontinuities in density and pressure. And you can see on the left what that grid looks like. So we've got the very dark black areas, there are thousands of grid cells, and the other areas, there are many less. And the solution's very smooth in those areas. And that not only allows it to work very efficiently, but it also allows us to only do work where we need to, and it also allows it to run very efficiently on a parallel computer. I'll come back to that later. The pictures I've been showing you are the kind of pictures that a computational modeler, a numerical analyst would draw, and are effectively plots of density and pressure, but they're not what experimentalists see. So I wanted to show you this. These are Schlieren images. They are photographs that show sudden changes in density. And the ones on the left, the hand-drawn one, was drawn by August Topler, who invented the Schlieren apparatus. And that predates you to being able to take photographs at the speed that you would need to take a photographic image. So he used a bright spark as the light source, and he stared down a telescope at the experiment, set off the bright spark, and then shut his eye so that the persistence of vision, where the image was burned onto his retina, he could then draw in his notebook. And that's how he drew that image that shows the shock in different positions at different times. And what's next to it is a colour Schlieren image that was done in 1995 by the Ernst Mach Institute of exactly the same experimental conditions. And I just think it's amazing that in 130 years later, someone's doing this and going, you can really see it. He also described Mach reflection in his Schlieren images, but the scientific world said, it's just what you say you've seen, there's no proof. And so they're not called Toepler waves, they're called Mach waves, which is a shame. But if we want to compare with an experiment, why don't we take our computer solution and use it to produce the kind of plots that experimentalists produce? So that's a computer-generated Schlieren image on the right, and the other one is a computer-generated holographic interferogram. So that's another experimental technique. Single Mach reflection and double Mach reflection. And just to show what else you can do with this, if you really want to get going with this, you can do chemically reacting flow. So this is some simulations that we did in the late 1990s with my first PhD student, Boyan Zhang, of the detonation of hydrogen and oxygen in nitrogen. And you can see the wiggly, crinkly front is a detonation wave traveling across the computational domain away from the point where the ignition has happened. That calculation ran for 2 weeks on the computer that we ran it for. And the first time we ran it, the computer crashed halfway through, so we didn't get any results. So we had to try again. So I want to talk about computers, but first, we'll have a bit more guidance from Lewis Carroll. He had 42 boxes all carefully packed, with his name clearly printed on each, but since he omitted to mention the fact, they were all left behind on the beach. I want to talk about some computers. There are 3 computers here which are very important to me. The first computer in the bottom is the Apple II computer that's like the one that my dad bought. And at the time that that computer was bought, if you wanted to play games on it, you had to write the game yourself or type it in from a magazine. It was very painful. So I learnt to program the computer, and I had a lot of fun. And then, having been interested in computer programming in my undergraduate degree, I did a sandwich placement, and I went to work for the Atomic Energy Authority at Harwell, where I got to use the most Star Trek computer I have ever seen, which is the one on the right. That's a Cray 2 computer. My mobile phone outperforms it significantly now. At the time, it was revolutionary. It was capable of 200 million floating point operations a second, which was very, very fast. Liquid coolant flowed over the circuit boards, which fluoresced gently in ultraviolet light. So Cray, of course, put ultraviolet lights in the storage tanks. So there was these nice blue glowing tanks at the back. And I should say that our one looked a bit like that, except the coloured fabric panels on it were a very nice cerise pink, because our system administrator, she was shown a colour chart from Cray and said, what colour do you want it? And she said, oh, I quite like that pink. So we had a pink computer. And she also then went to war with the Civil Service Works Department, and with the Civil Service colour chart, which had about 3 colours of varnish and a choice of magnolia and white walls, managed to decorate the machine room so it blended in nicely and contrasted with the pink computer, and got a row for painting skirting boards a colour that was only used for post boxes. The other computer up the top is Archer 2. That's the supercomputer that the university runs on behalf of the UK academic community, and it's just about to be replaced, and I don't know what the new computer is going to be called, but it's going to be a lot faster than that one was. So I want to talk about computers and calculation. So if we want to do z equals x plus y, the computer has to go through these steps. It has to fetch the instructions from memory and the data that it's going to operate on. It has to decode them, so effectively it has to look at the plus symbol and go, oh, I'm supposed to be doing some addition. Then it has to execute that, and then it has to store the results in memory. And it has to do it again and again and again. And if we want to do it on a vector, and we want to do it on a vector on the Apple computer, then you have to do that fetch, decode, execute, store thing, and then do it for the next one, and then do it for the next one, and then do it for the next one. The computers are really good because they're very good at mindlessly doing the same thing a billion times, but that's quite slow. And so Seymour Cray had the idea of building a pipeline. So you could have a bit like a sort of production line that did the calculation, so that once you fetched it, the bit of architecture that does the fetching starts fetching the next instruction while the next bit of the production line does the decode and the execute. And it looks a bit like this. The Cray 2 had a vector length of 512, so it could do 512 of the same calculations in this production line. And you had to program it like that. And it made it very fast. It's not perfect, because if we need the result, we haven't done the calculation, so we don't have to wait for the store, but we can't keep doing things in the vector pipeline very efficiently, so everything's very slow, and we say it won't vectorize. And we also have a problem because if we've got logic in there and tests, we might not be interested in the result of some of the calculations we've got, so we might have to throw out some of the vector pipeline. And so doing things like this makes it difficult and complicated to program to get it really efficient. This is not what computers like Archer 2 do. Archer 2 is a parallel computer, and so you split the calculation up amongst lots of people. If I imagine that I wanted to do 1,000 calculations and I asked you all to do a few of them and gave you all a piece of paper and said, do these calculations, and when you finish, give me the answer, that's what the parallel computer does. So we've got lots of things doing fetch, decode, execute, store, and then they're communicating. The problem that we have is that communication is very, very slow compared to computation. And most of the effort in designing supercomputers doesn't go into making the computation unit run fast. It goes into making the communication as efficient as you can make it. And unfortunately, a computer scientist called Amdahl stated that eventually communication dominates and you can't go any faster. So throwing more processors, it doesn't get you any further. Just to give you an idea of how bad that gets, here are 3 processors doing something. And the first processor sends a message and the other 2 receive it. And then they start doing some calculations. And the first processor finishes its calculation and sends something, but it needs an answer now, so it's going to wait. And it's going to do nothing until it gets the answer back. The other processors are doing calculations and sending and waiting, and everything's going on until eventually we get to the end of the calculation. And in this simple example with 3 processors, my 3 processors are only doing useful work half the time. So I've got 3 processors. The calculation's not running 3 times faster. It's only running 1.5 times faster. So I need to think about that. And it gets worse to think about as you have more processors. And Archer 2's got 750,000 processors. So if you wanted to really parallelize your job, you've got to make sure that you've not got communication hold-ups when you're trying to send messages between 750,000 processors. And this means that it's all in the coding. The graph that's up here shows a computer code. It's actually the Amrex one that I was using for shockwaves, running on thousands of processors. So we've got a number of cores, number of processing units on the bottom, and that goes up to nearly 10,000. And you can see that as we add more processors, the time to do a time step comes down, because that's what's on the vertical axis. But eventually, the line goes horizontal, it's saturating. Adding more processors is just meaning that more processors are spending more time not doing anything. So we need to think about that, and communication is dominating in this. The other thing about coding that's very important is that if you write code well and you think about the architecture of the computer that you're running it on, you can write code that's about 12 times faster than the average code that the average programmer will write. This is a bit like deciding that you want to go Formula One racing and turning up with a milk float, because that's what a lot of programmers will do. Now, Moore's law, which you've probably all heard of, tells us that the speed of a processor doubles every 2 years. So a simple bit of mathematics tells us that we have to wait 3 years and 7 months to buy a computer which is 12 times faster. It's probably going to cost us a lot of money, and it may have been easier to write the code well in the first place. How long should my simulation run for? Well, here are some suggestions. All of these are useful suggestions, maybe apart from having to go on holiday while it runs. But if it's running in 20 minutes, you can go and get a coffee. If it's running for an hour, you stick it running at lunchtime, get some lunch, come back to the office. If it runs overnight, that's really good because there's no subjective time, you just wait. Over a weekend's a bit more painful because you only get to run the code once every 7 days. And if it takes 7 to 14 days to run, then you're going to be on holiday or you're going to be sat at your desk sleeping while your boss thinks you're working. It's not very good. And as I said before, it's important to save intermediate results because otherwise when the lab burns down or the computer catches fire, you've got a problem. Okay, now, I work in the Institute of Energy Systems, so I was thinking about all this stuff about efficiency, and I saw this. This is the energy mix, actually it happens to be on the 4th of April in the UK. So all of the electricity that we were generating on the 4th of April is on this graph and where it was coming from. And this is publicly available data that you can download and process. So you can see that some of it was coming from wind, some of it was coming from nuclear, some of it was coming from coal and gas and biofuels and biomass and stuff, and that's all emitting carbon. So the other thing that you can do with this graph is you can look at the carbon intensity. So on the 4th of April, between midnight and midnight on the 5th, that's how much carbon was being emitted per kilowatt hour of energy on the UK grid. So if you plugged in your 1-bar fire and turned it on, that's how much carbon was being emitted to warm your house with that nice, clean, green electricity. Okay, so on average, we used 113 grams of CO2 per kilowatt hour on the 4th of April. Let's pretend that I ran a calculation on Archer. Archer uses about 3.2 megawatts of power. That's about how much it draws to run the computer. It's near the town of Pennycook, and that's more electricity than the town of Pennycook uses. And if we work that out on that day, it comes out to be about 64 kilograms of CO2 an hour. And that's about 50% more than a Boeing 737-400 emits in flight. Okay? So an hour of computer time, I could have had an hour's transatlantic flight of that. If I'm not using the whole machine, it might be a bit better. So if I have an unoptimized calculation that's running on 32 nodes of the computer, it runs for 12 hours, it's going to emit nearly 24 kilograms of CO2. That's quite a lot. Now, our current car is an electric one, but prior to that, we had a diesel Skoda, and that emitted 112 grams of CO2 per kilometre. And so that's equivalent to driving to just beyond Inverness, that amount of carbon. But if I'd optimised the code and it ran 12 times faster, it's not even driving 20 kilometres. So I say to people they've got a duty to make sure that their code is written efficiently. Not because it's going to run faster on the computer, but because the same calculation is going to use a hell of a lot less carbon. And if you believe in a revolution in reducing the amount of carbon that we're emitting and climate change, then we have a duty to write efficient computer code. And many, 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 many of my colleagues grab a computer code off the shelf and throw stuff at it until it works and don't think about the efficiency of it. Maybe we shouldn't be doing that. Okay. Change of topic. While he was seeking with thimbles and care, a bandersnatch swiftly drew nigh and grabbed at the banker, who shrieked in despair, for he knew it was useless to fly. This are some pictures of sailing and diving. There's a discontinuity in these pictures. What is it? It's the sea. We've gone from the air to the sea, or the bubbles in underwater. There's a massive change in density and viscosity when you go from air into water. My family accused me of taking lots of pictures of waves, so here are some pictures of waves that I've taken. They show how dynamic that is. Breaking waves, spray, foam, all sorts of things going on. And if we want to try and model that, then we're going to have to think about it. So we've got a free surface, and I'm very grateful to Jorge Sandoval, who's in the audience. He's my current PhD student, who drew this lovely diagram. So we've got, as we go down from air into water, we go from pink into blue, then the density changes by a factor of about 900, and the viscosity changes by a factor of about 100. And then that water surface is subject to gravitational forces, so we might get tsunami waves, very, very long wavelength waves caused by earthquakes. We might get tide waves, the very long period waves that are created by the orbital mechanics of the moon and the sun around the Earth. Or we might get wind-driven waves of the kind that we normally see when we go to the beach. And we want to solve those equations, we want to do something, and we can do this in different ways under different conditions. And the first set of conditions that we can look at are shallow waves, shallow water waves. And in a shallow wave, the wave can feel the bottom of the ocean, can feel the seabed, and if the wavelength is very long compared to the water depth, then we can approximate this with a set of equations where we're only going to solve for the water depth and the velocity. And we can simplify everything, and we can do it really easily. And the good news is that we can do that using exactly the same shock capturing methods that we used in aerodynamics. So here is a simulation of water in a channel with a Bohr wave propagating down the channel, and I've got single mark reflection, just the same as I would have had in the gas dynamics on one side, and on the other side, it looks like it sort of overflowed the top, and that's because that's a sloping wall, and the water's come up the sloping wall and overtopped it, and we've got wetting and drying going on the top of the wall. So this is a bit like what you might have if you had the 7 Bohr propagating down a channel, and the channel came in suddenly with sharp concrete walls. We can see that a bit better if we look at something like this. This is a channel that's got curved walls at the entrance and then a straight section, and we get that lovely diamond pattern of shock waves in the channel as it converges. The very bad, very grainy photo on the left is a photograph from 1951 from the original experiments that were done by Ippen and Dawson in the States. That's so we can do that. Now, the other thing that we can do with shallow water is tide waves. So those the tidal effects have a very, very long wavelength compared to the water depth. So we could do a simulation of the tide flowing around islands in Scotland. And these simulations were done by Brian Suller and some of his colleagues of shallow water and tide. And there's an important model of a tidal turbine in here. And you can see the wake of the tidal turbine in this layered shallow water model. And this all runs relatively quickly, it's relatively easy to do, and you can do a large geographic area, so we've done all around the Orkney Islands to do this simulation. So we can get a long way with shallow water waves and shallow water equations, and we can do a lot of things with them. But we might be interested in what the free surface is doing itself. So if we're going to solve for the density as we go through the free surface, we're going to have grid cells, a bit like the one that's drawn at the top here, where there's a mixture of air and water in that cell. And we have to do something with that. And we can use a technique, the shock capturing techniques again, to solve the equations in that way. Where we've got a mixture of air and water in a cell, we're going to have a problem that is going to cause some mass and momentum issues. But we can do that. And this is a computer simulation running on the right-hand side, and some experiments that Tom Bruce did in the Large Wave Flume in Barcelona on the left-hand side. And this is, the computer simulation is one of those waves. So we can see the wave breaking, and the breaking wave impacts on the seawall and goes over. And this is a bit of a cheat, this animation, because I've solved for density, so the density is going between the density of water and density of air, and I've just coloured it so it's blue if it's in the water, it's black if it's in the air, and if it's got a mixture of air and water in it, it's white, so it looks a bit like the spray on the top of the water thing. So it's a bit of a cheat. We're solving those equations everywhere, in the air and the water, so that's the velocity field that I solve for. Only about 20% of the domain is underwater, so I've done a huge amount of work to solve in the air when I might not have been that interested in it. Interestingly, in this case, we were interested in the speed of the jet of water, and that turned out to be about 5 times the speed of the wave coming on shore, and that was in good agreement with the experiments. Though I think William, who's in the audience, has done experiments where it's been like 20 times the initial wave celerity, so even bigger. However, I'm not going to talk about wave overtopping in detail because we're talking about numerical analysis and mathematics. So instead of doing that, we can solve equations using a level set method. So what we're going to do is we're going to introduce a function, which we just call phi. It's just a Greek letter that stands for something. And phi is going to be positive if we're in the water. It's going to be 0 where the free surface is, and it's going to be negative if we're in the air. And that's good because we can just solve for that 0 contour anytime we want, and we know where the free surface is. And we can solve Navier-Stokes equations for the quantities. And we're going to only solve the flow equations in the water, and we need to do things to make sure that mass is preserved and that phi has the right mathematical properties, so there's a bit of complexity going on there. And then everything needs to be done in parallel because it's going to run in parallel across some computers. And the idea that we're using something called a ghost fluid method. So we need boundary conditions just above the water, and what we're going to do in those cells is we're going to predict the values of the quantities in there so that the free surface does what we want it to do. And we need to enforce 0 tangential shear and constant pressure and surface tension and stuff in there so it behaves well. Hopefully this is a lot cheaper than solving in air and water because we're only solving in one fluid. Just to show you how it works, this is the solution for what's called a Stokes wave. And you can see the blue ones are calculated and the red ones are the boundary conditions. And the blank cells above that, we're doing nothing in. They're there in case they get filled with water, but we're doing nothing otherwise. So we're doing a lot less computational work, and so the method runs faster. And what Jorge's been trying to do is to do simulations of shallow water flow towards a block. So we've got the wake around the block, and on the left-hand side of that, you've got some experimental photographs. And on the right-hand side, you've got some simulation results that show that bow wave forming in front of the block. If you've been for a walk by the water of Leith and you've looked at the bridge piers when the water's flowing quickly, you will have seen exactly this kind of flow phenomena around those bridge piers. Okay. There's Thingamabob shouting, the bellman said. He's shouting like mad, only hark. He's waving his hands and he's wagging his head. He's certainly found a snark. Let's talk about tidal turbines. The video at the bottom is the orbital O2 tidal turbine in Orkney, in the water. It's stationary. Okay? It's stationary. I'm on a boat when I shot this video. The boat was doing 7 knots upstream with the engines being thrashed to stay in steady position next to the tidal turbine. And there's a few waves on there, but they're not very big. Above that, we've got the Sabella tidal turbine, which Brian did a lot of measurements on and spent a lot of time in Brittany attaching instruments to. And then on the other side, we've got the Sustainable Marine Energies platform. So these are all tidal turbines of different kinds. And if we want to know how a tidal turbine works, then we need to do some experiments. So this is a flow wave experiment that was done with a single turbine. We've also done them with arrays of turbines. And we've got turbulent flow onto that rotor. We've got waves onto the rotor, and all of those are moving the rotor in an unsteady way. That rotor is driving a generator. And the generator is being controlled by a controller to make sure that the right amount of power is coming out of the generator and into the grid. And so if we want to get this right, we need to make sure that the fluid processes are modeled properly, the mechanical processes are modeled properly, and the electrical system is modeled properly. And the electrical system feeds into the mechanical system, which feeds into the fluid dynamics, so we have to do it closely coupled together. We can't just do it one way. And so that's what we've tried to do. The boundary conditions for this come from measurements, and this is Brian's measurement equipment. There's 3 tons of concrete there, and the 3 tons of concrete is supporting an instrument which is about the size of a cake tin and weighs about as much as a cake tin. But you need 3 tons of concrete or it moves around on the seabed and you don't get proper measurements. And then these are the kind of measurements that you get. That's going up through the water column, and you can see big waves coming along. That's 60 meters deep, and you can see the waves go all the way to the bottom, and there's also a lot of turbulence in there. So we need to make sure that our simulation is dealing with this. Okay. So what we did was we took all of that data and we analysed it, and we also included data that had been taken from EMEC, and we did a whole load of comparisons, and we managed to identify a set of test cases that we could do in FlowWave to simulate the behaviour of a turbine under realistic conditions. Or I should say we did. I didn't do any of that. The very clever people that run FlowWave did. And then they took lots and lots of measurements. This grid shows you where the measurements were taken in 2D. There are also measurements off to the side. Each one of those spots was measured using an ADV, which is an acoustic instrument. Each one of those spots takes 20 minutes of measurement. So the experiment's running and the ADV sits there for 20 minutes, then it gets moved to the next spot. So it takes a long time to collect all this data. And at the same time, they're also measuring the forces on the monopile and on the rotor and all sorts of things. So we get experimental time series like this. And this has been post-processed and quality assured by Jeff Stainer, so I'm grateful to him. I'm showing you that because we want to try and do that in CFD. We want to try and do a computer simulation of this. And so we need to model the turbine. So here is the CFD model of the turbine. We are going to have a model in our CFD code which takes the flow field and takes the forces out of it where the blades are. We're going to do that using something called blade element momentum theory so that we're not having to actually resolve the blades in detail. But that's all fixed into a generator model that goes all the way to the grid. And that electrodynamic model is very important. This code was run, these simulations were run by Arturo Ortega, who's a postdoc working with me using code called OpenFOAM. It worked quite well, but I dislike OpenFOAM because it's not very efficient on high-performance computers. So this is a case of don't do what I do what I say. Okay. This is the electrodynamic model, which was developed by Jonathan Sheck and Marius Sunis. Which we fully coupled into the CFD solver, and these are the results. So we're starting with the turbine stationary, and you've got turbulent flow coming onto the rotor, and the rotor starts to spin in response to the forces on it, and then you can see the wake developing behind it as the rotor spins. Now, we've not got the support structure in the CFD simulation, so there's stuff that we're not simulating, but we're doing the rotor going round. And that rotor is connected to the generator, and we're getting all of that electrodynamic information out of it. Okay. So we can look at the results like this in a bit more detail, and we've got a slice here through the rotor looking down from above, and we've got a slice through the rotor looking at the end of the rotor, and you can see all that swirling colours of red and yellow, which is the turbulent field going past it. And we can look at the measurements of thrust and torque and power that we were getting from the simulation, and we can compare those with the thrust and torque and power from the experiments, and we can see that we're within about 5%. So it's pretty good accuracy for the model and the simulation. These simulations for a few minutes of simulated turbine operation run for about 3 days on a supercomputer. So they're expensive to do. We can change turbine though, and so this is the Sabella turbine with its 5 little stubby blades being simulated, and again we were in about 5%. And the important thing that we get out of that is that we get graphs that look like this. So the red line here is the simulated electromagnetic torque on the generator from that CFD simulation. The blue line that's on there results from a design code which is using the same electrodynamic model of the turbine, but is just using a very simple model of the hydrodynamics that doesn't have the turbulence and all that kind of stuff in it. And you can see just how much noise there is in there. And we can look at the variance of that and the statistical properties of that. And that's very important for the designers of the turbine. And it's very important for the designers of the power electronics, because this electrical noise is going to age those components quite quickly. And they need to know how long they're going to last, what their fatigue properties are and things. So we can do that from this kind of simulation. So that was the sort of state of the art in turbine simulation. Where do we go next? Well, if we really want to do this properly, then we've got to do braking waves over the tidal current, because when the tidal current's very strong and waves are going in the opposite direction, the waves steepen and break, and we're not modeling that in there. In fact, in those simulations that I was just showing you, there are no waves. So we really need waves. We need an accurate free surface model of the kind that I was talking about that Jorge's been working on. We need to model the floating supports for the structure. So there's effectively a boat there with turbines on it, and we've got to model that. And that is, although it doesn't look like it's moving in the video, it is moving about a bit in response to the waves and the turbulence and the tides. We need to model the moorings and the tension on the moorings and make sure that the station keeping's right. We need realistic turbulent flow coming in. So there's lots and lots and lots and lots of things that we're not modeling in here. So there's an important question to ask yourself, which is, how much physics can I afford? This is not lots of the physics that I was just talking about. This is just fluid dynamics models. So the simple potential flow model that was that blue curve, you could run it on a tablet or a mobile phone. It's really, really cheap to run. But if we want to go up to very large eddy simulation and detached eddies and direct numerical simulation, if we could possibly go there for this problem, then that's massively expensive, and we're going to be using some of the biggest supercomputers in the world for a long time to do these calculations. Maybe we want to do that. Maybe we just want the badge that says like world speed record for supercomputer or biggest amount of supercomputer time used for fluid dynamics calculation, and there are such prizes. You know, there are such prizes. There are people in the audience who will wish to win the Bell Prize for supercomputing applications, and maybe that's a good thing. But maybe we can do it cheaper. Maybe we can do it with a more efficient model. And we have to think about: are we doing something because we want the bragging rights of that really high performance computer calculation? Are we doing it because we want a really detailed understanding of physics? Or are we doing it to help the engineers design something better? And do the engineers need to wait for 3 months while the supercomputer does its stuff, and then for another 6 months while we try and work out what the results that we've got back mean? Or would they be happy with something that ran in an hour on a laptop computer? So it's something to think about. So we've come to the end of our adventure. I want to finish with something about coming home. So the first land we sighted, it was called the Dodman. Then Rains head off Plymouth and start Portland and White. We sailed by Beachy to Fairlight and Dover, and then we bore up to the South Foreland Light. It's one of the verses of a sea shanty called Spanish Ladies, which I've decided not to sing. You'll be pleased to know. It's about coming home, having sailed from Spain back to the UK in the Napoleonic period. But it mentions a lighthouse. So I want to finish with this photograph. Faire dans le tempête la jument. It is probably the most famous lighthouse photograph in the world. It was taken by a French photographer called Jean Guichard in 1989 of a lighthouse in a storm. And you can just about see there the lighthouse keeper stood in the door of his lighthouse watching the helicopter that appears to be buzzing his lighthouse with some mad photographer leaning out of it taking photographs. It's a brilliant photograph. It won Jean Guichard a load of prizes for photography, and it won, it won top awards and stuff. But I really love this photograph because it's got all the physics that we've just been talking about in it. So we've got a slamming wave impacting onto the back of the lighthouse. That wave is reflected, so we've got complex wave reflection. We've got wave breaking. This is the incident wave down here, and we've actually can see mark stems from mark reflection of that wave impacting on the breakwater around the lighthouse. And we've got spray and aeration and all sorts of complicated physics, and we've got a keeper. So I just want to finish with this. The other point to make here is that this lighthouse is 5 nautical miles from where the Sabella tidal turbine was put. So if the lighthouse is subjected to this, just think what happens to that tidal turbine and why Brian's measurements have such big waves that go all the way to the seabed. But that's where I want to leave you. I hope that's been an interesting adventure and you've enjoyed it as much as I have. Thank you very much.
Thank you very much, David. That was fantastic. I loved, see, I'm a mathematician, so I only normally just see the equations. I never see any of the applications or the fact that this actually has real life data and incredibly important thoughts around energy and things like that. So thank you so much for this. It is a tradition that we are continuing to develop, that we will have an opportunity to ask David lots of questions over drinks and something to eat. That will be waiting for us outside. So I would like to thank David again. I hope we will all do that, and to thank everybody who's been online as well to take part in this. It's great to see how this stretches across all of the world as well. So thank you very much, David. Thank you.
Thank you.